Yeah, a nod or something. Yeah, brilliant. Thank you. So yeah, no, thank you very much for inviting me to give a talk. This is the first time I'm going to be giving this talk, as I mentioned to some of you earlier, and so I'm expecting it to be about somewhere between 30 and 45 minutes, but because it's the first time I've done it, and I've not had a chance to kind of run through it myself, actually, I'm not entirely sure how well the timing is going to work. I promise you that I won't go over the 7 o'clock, which of course is when Boris Johnson's going to be telling us about what we can do in terms of over the next few weeks when maybe lockdown starts to ease a bit. So I won't go that long. And so, yeah, like I said, I'm expecting it to be somewhere between the 30 minutes, 45 minutes mark. Okay, I really hope it's not like only 10 minutes. It shouldn't be anyway. So yeah, so I do research into active galactic nuclei, and so we'll cover that a little bit in this topic. So I won't tell you at the moment just what active galactic nuclei are, and so well, actually I'm going to have to now. So active galactic nuclei are related to black holes, and so but what I'm going to give you in this talk is more of kind of summary of like the discovery of black holes and why we think they're so important. Okay, so this is an area of astrophysics, or actually an area of physics, which has received a great deal of attention over the past few years. Now, hopefully you can see my slides if I flick through. So you should be able to see my slides there. So I've now just moved the slides onto, you can see like two black dots in the top left and a kind of a golden dot in the top right. Okay, so hopefully you can see those. If you can't, give me a shout, because clearly something's gone wrong, but if that's the case, then that's fine. And so yeah, over the past few years, there's been some major discoveries in the area of black hole physics. Okay, and so in 2015, there was the first discovery of gravitational waves by the LIGO gravitational wave detector based in the US. And then in 2019, there was the discovery, or well, there was the observation of the event horizon of a supermassive black hole. And this was performed by connecting together lots and lots of submillimeter telescopes, which were located all around the world. Okay, and they effectively made, by joining all of these telescopes together, they effectively made a telescope that was as large, had the resolution of a telescope with a diameter roughly that of the Earth. Okay, so huge. By using this technique, they effectively made a huge telescope, and in doing so, they were able to achieve this resolution, which allowed them to observe a supermassive black hole in a nearby galaxy, which is M87. And then last year, we had the Nobel Prize, which was awarded to 3 scientists, 1 theorist, 2 observers, 1 based in Germany, 1 based in the US. And they were awarded the Nobel Prize because of the work that they've been doing over, well, in the case of Roger Penrose, over the past 60 years on black hole research. And then for the observers, for the work that they've been doing for about the past couple of decades. Okay, so it's very much regarded at the moment that we are going through a real a golden age in terms of black hole research. I should also mention, of course, that the detection of gravitational waves from 2 colliding black holes, that also received the Nobel Prize, I think either in 2016, 2017, that kind of time. Okay, so it's very much a kind of a very active area of research. And of course, it's one of these areas in physics and astrophysics that really does attract a lot of attention from the media and from the general public in general. So I'm very fortunate to work in this area, which kind of gains this so much attention. And it's very kind of exciting area to work in. But in this seminar, what I'm going to talk about is I'm going to talk about the discovery of black holes. I'm also going to talk about how they've graduated from being essentially like a curiosity when they were first proposed and they were first discovered. They were very much seen as sort of like a curious feature of the universe. But now they've graduated into what we believe to play a very fundamental role in how galaxies have formed and evolved over the past 13, 14 billion years. Okay, so they're no longer just regarded as sort of like a passive player in our understanding of the universe. They're very much regarded as something that is very important to our understanding of why the universe looks the way it does. But to consider that, the first thing we're going to do is we're going to go back around 200 years, okay, because that was when black holes were first proposed. So amazingly, they were proposed back in the 18th century by a man who was at the time, like a lot of people, he was actually a member of the clergy, but the clergy at this time were essentially the most highly educated people at the time, because they had to go away and study and learn to read and became very literate, and so they also tended to have a lot of interest in other areas of research. And there's this guy called John Mitchell. And what John Mitchell, after having kind of read up on Newtonian theories of gravity and Newtonian dynamics, he proposed this. So he proposed that if there should really exist in nature any bodies whose density is not less than that of the sun, and yet whose diameter is more than about 500 times of the sun, then their light could not arrive at us. What he's basically saying here is that if you took something that was the density of the sun, and if you made it larger and larger and larger, eventually you would get to the point whereby the surface gravity at the boundary of that object would be so high that not even light could escape. Okay, so we can have, and so I should, I think as mentioned at the start, I'm going to use my blackboard a couple of times. Okay, and so because I think it's quite nice for you to see where some of these concepts come from, and so this is the first time I'm going to be using the blackboard, and so what we're going to do is I'm going to kind of work out what the radius of an object would be in order for that to become a black hole. Okay, and so what we can do, we can use Newtonian dynamics for this. And so what's the nice thing about giving a talk to people who are doing physics at university is that you understand, or you're familiar with a lot of the concepts or the equations that I'll give. I'll just tilt my screen up so you can see the top of my head. There we go. And so what we're going to do is we're just going to equate, so how you would work out the escape velocity of something is you equate the kinetic energy of an object with its potential energy. Okay, and as I say, for this we can actually use Newtonian dynamics. And so if we treat light as being made of particles that are traveling at the speed of light, okay, and of course those of you familiar with relativity will know that this isn't the correct thing to do, but like I say, it works out anyway. We can say that our kinetic energy is 1/2 mc squared, where c is the speed of light. We can say that that is equal to so the potential energy, okay, for this object, whereby the escape velocity is the speed of light. Okay, so that is equal to dm over r. Okay, so that's potential, the gravitational potential. We can cancel out our m's. Okay, and then if we rearrange this, we can say that, well, if r is equal to 2 gm over c squared, okay, then light wouldn't be able to escape from the surface of this object. Okay, this object of mass m has got a radius of r, or radius of r or smaller. Okay, then light would not be able to escape from this object. And so now that we know, these days, now that we know what the speed of light is, okay, we can actually work out what radius this would correspond to for objects of different mass, and we also know what g is, our gravitational constant. It turns out, for something with the mass of the Earth, for the Earth to form a black hole, it would need to be equal to about, or smaller, around 5 centimeters. So you can imagine that should give you some kind of sense of how dense an object a black hole has got to be. Okay, and it's when we talk about just black holes and mention this word, it really isn't. I think you don't really grasp how extreme these objects really are. If you just think about it, like if you've ever been on like an intercontinental flight and you've really got to experience how large the Earth is. You take that and squeeze it down. You have to squeeze it down to something 5 centimeters in size in order for it to become a black hole. If we're talking about something the size of the sun, that corresponds to taking the whole sun and squeezing it down to something that's around about 3 kilometers in size. Okay, and so that's if we wanted to turn the sun into a black hole. Okay. So there you go. So I wanted to show you. I wanted to do that to show you just how extreme a black hole is, because it's very easy, like I say, to bandy about these words and not really get what it actually means. Okay. So as I said, so that was using Newtonian dynamics, but actually you get exactly the same result as that if you use relativistic equations as well. Okay, and so at the time when John Mitchell and for a number of years after that, when this was proposed, people presumed that this was impossibly small. Okay, these objects were impossibly small, and so it very much stayed within the realms of theory. Just, well, yeah, maybe these things could exist, but how on earth would you take a mass the size of the Earth and squeeze it down to something so small that it would meet these criteria? Okay, but what really helped with the progress of black holes was actually the first discoveries of white dwarfs, so white dwarf stars. Okay, and that's because when we observe white dwarf stars, when we observe some of them, we find that they are formed in binary systems. And if you have a star in a binary system, you can work out what their masses are. And so these discoveries of white dwarfs happened at the start of the 20th century. And as I say, by having these binary stars, these binary white dwarfs, we were able to work out what the masses of these white dwarfs were. And it turns out they've got a mass of roughly that of the sun. Okay, so fair enough, that might not be so interesting. There's lots of stars that have got masses of roughly the sun. However, when they studied these objects more carefully, what they realized was that the radius of these white dwarf stars is roughly that of the Earth. Okay, and you had stars that have got masses of that of the sun, and yet they are extremely compact. Okay, so far more dense than our sun and other typical stars. Okay, and what was realized at the time was that the only way you could have a star that had such a tiny radius compared to given its mass was that it was being held up not by typical forces like you have in the sun. You have convectional forces and you have radiation pressure that's pushing out and balancing against gravity. That's not happening in a white dwarf. Instead, it's being held up by what's known as electron degeneracy pressure. And that's basically a quantum mechanical effect that kind of says that we can't have all of the particles within this object all in the same quantum state, okay? And so they're actually supported by quantum mechanics. Now, around about the 1930s, a guy called Chandrasekhar determined that if you have a white dwarf which has got a mass of greater than about 1.4 solar masses, then this quantum degeneracy wouldn't be strong enough to keep these stars supported. Okay, and so what would happen after if a star exceeded this 1.4 solar masses, Other people proposed, so Bard and Zwicky proposed that it would move to an even denser state. And that denser state is what is known as a neutron star. And so neutron stars were confirmed in the 1960s by Jocelyn Bell Burnell and her collaborators. And so they've now been known for roughly 50 or 60 years. And what's known about neutron stars is that, as Chandrasekhar and Bard and Zwicky predicted, they are far, far more dense than white dwarfs. And so, to give an example of what a neutron star, so instead of having a solar mass crammed down to something the size of the Earth, a neutron star has got a solar mass, or roughly a solar mass, crammed down in something that's only about 10 kilometers across. Now, a guy called Oppenheimer, who actually is most famous for the work that he did on the atomic bomb during the Second World War, but what Oppenheimer came about and realized is that actually, as you do with a white dwarf, there was an upper limit to what your neutrons, to the mass that your neutron star can have, and that's roughly about 2.5 solar masses. If a star is larger, or if a neutron star becomes larger than 2.5 solar masses, then ultimately it will collapse to a black hole. Now, this is what most people think of in terms of black holes. When you talk about black holes, what people typically tend to think of is something that is like a dead star. Okay, a star that is effectively collapsed in upon itself. And what I'm showing here is an artist's impression of
James,
what...
I'm really sorry to interrupt. Would it be possible to try and make the PowerPoint full screen? I don't know if it's visible to everyone else.
Is that better, or?
Yeah, that's a bit better.
Is that a bit better?
Yeah.
I can make it a little bit bigger. That's about the biggest I can make it.
Yeah, that's really good. Sorry about that. Thank you.
That's all right, no problem at all. Yeah, so this is what most people, an image like this is what most people think of when they think of black holes. They think of a collapsed star. Okay, and here for comparison, we've got another star next to it that is feeding material onto this black hole, and actually the black hole would indeed be actually be a lot smaller than what we see here compared to the size of this star. And so even this is quite an exaggeration of what the actual physical size of a black hole, a stellar mass black hole, would actually be. Okay, and so what we have here is we have this material falling and we're forming what's known as an accretion disk, and we'll look into accretion disks a little bit later, and so onto this black hole towards the center here. But I should say, and so these stellar mass black holes, people by making X-ray observations, people believe that they were seeing these stellar mass black holes roughly in the 70s and 80s. But they were finally absolutely confirmed with the detection of gravitational waves, these stellar mass black holes as they've become known. These were finally confirmed with the detection of gravitational waves in 2015. However, the first hints of the existence of black holes happened far earlier, even before the first X-ray observations of stellar mass black holes. And those first hints didn't come from stellar mass black holes. They came from a different beast entirely. And the first suggestions of these different black holes came in the form of radio astronomy. Okay, that's how they were first detected. Okay, now radio astronomy, if you're ever interested, the development of radio astronomy is actually a fascinating tale. Before I became an astronomer, I was actually going to go and work for a company called Kinetic to work on like their radar systems. Now, the development of radio astronomy is very closely related to the development of radar, and if you can kind of get a book on it, or kind of attend a seminar on the development of radio astronomy, it's absolutely fascinating. But unfortunately, I haven't got time to go into that now. Okay, but After the Second World War, a lot of the technicians who worked on radio technology, so in particular the development of radar during the Second World War, they moved after the wartime. They moved into, or some of them moved into radio astronomy. Okay, and they worked on this during the 1940s and 1950s. And at the end of the 1950s, radio astronomy had reached a point where they were able to start making observations of distant objects. Okay, and so they released a catalogue known as the Third Cambridge Catalogue, and that was because it was done by astronomers working in Cambridge. And so that was released in 1959, a catalogue of radio sources across the whole sky. Now, at the time, the problem with radio astronomy was that it had extremely poor resolution. Okay, and so in other words, you detected something in the sky with your radio telescope, but you could only pinpoint it to within a few degrees. Okay, whereas if you want to match it with something in your that you're doing with optical astronomy, you need to be able to pinpoint it to within a few arc seconds, okay? And so roughly 1/3600th of a degree, okay? And so you've got very poor, at the time you had very poor resolutions with your radio telescopes. How they got over this, or how they overcame this, was actually using quite an interesting technique. And so what they did, astronomers at the time, they used moon occultations to measure the position, the accurate positions of radio sources in the sky. And so what they would do is they would try and point their radio telescopes to somewhere in the region of where the moon is. As the moon passed in front of the radio source, very suddenly your source in your radio detector would disappear. Okay, its flux would disappear to zero. And so when that happens, if you knew the position of the moon at that time, you were able to pinpoint to within the size of the moon, the source of your radio, or the location of your radio source. Okay, and by doing this technique, astronomers were able to pinpoint a particularly important, in the history of black hole astronomy, a particularly important object. That object, oh sorry, I'll skip that slide. We'll move on. There's no need to show you that one. So the object is this, what I'm showing in the slides here. Okay, so this is an object known as 3C273. And so it appears in optical astronomy. So as I said, we're using this moon occultation approach. We were able to pinpoint the location of this radio source, and then once we knew what the location was in the radio, we were able to look at this patch of sky with our optical telescopes, and this is what we saw. We saw what looks like a star, quite a bright star. Okay, so fair enough. All that means is that we've got a radio loud star. Okay? However, in 1963, an American astronomer, he was actually a Dutch astronomer that moved to America, a guy called Martin Schmidt, measured the redshift of this object. Okay, and so redshift is a measure of how quickly an astronomical object is moving away from us. Okay, and he found that the redshift of this object corresponds to a number of 0.153. Now, redshift is proportional, as we know from Hubble. Redshift is proportional to distance. Okay, and so it turns out that if you take the redshift and I don't need that. There we go. If we convert that redshift into a distance, it corresponds to, let's have a look here, we've got it here. I've not written it in my notes. Sorry about that. Oh no, I didn't write it in my notes. It's several billion light years away. This object is 7 billion light years away if you convert that redshift into a distance. Now, if you know the distance of something, you can also work out its power. Okay, and so you measure how much energy our telescopes are picking up from these objects, you know how far away this object is, and so you can convert that into a total power, also known in astronomy as a luminosity. When we converted our flux using its distance into a luminosity, we realized that 3C273 has got more power than the Milky Way, is emitting more power than the entirety of all the stars within the Milky Way. But, as I say, it looks just like a star, okay? So, whereas normally we'd expect a galaxy to look like a galaxy, this just looks like a very bright single point in the sky. And not only that, but this thing varied in its flux over periods of roughly a day. Okay, now in astrophysics, if something varies, okay, and if it varies over a certain time scale, then that means it can't be any larger than the speed of light multiplied by that time scale. Okay, so if this thing's varying by over time scales for about a day, it means that this thing must only be roughly a light day across. Now, a light day is something, it's around about the size of our extended solar system. So just imagine that. Imagine the situation that astronomers at the time were in. They were in a situation whereby all of this power, so the power is a power equivalent to the total output of the Milky Way, all the stars in the Milky Way, a trillion stars in the Milky Way, is coming from a point in 3C273 that's roughly the same size as our solar system. So this caused a lot of problems. How on earth do you reconcile this? How would you get so much power from something that is so small? And so you can't use nuclear fusion, okay? So that's what people at the time had become used to. They'd become used to the idea that stars, like our sun and all the other stars, are powered by nuclear fusion. But that simply doesn't work with this. It's too compact and too an efficient system. What we can use, however, is gravitational processes. Okay, and so gravitational processes are able to generate more power more efficiently, okay, than nuclear fusion alone. And so what they realized, was what some people proposed, was that rather than these very bright sources being due to stellar processes, they're actually due to gravitational processes. Okay, and what can do this is material falling onto a very massive object. And what happens is, as this material falls onto a massive object, okay, it speeds up. So just in the same way that a satellite or an asteroid, as it crashes into a planet, it is attracted by gravitational waves. Attracted by gravity, it gets faster and faster and faster. And as it gets faster and faster and faster, the frictional forces build up. The material, as it falls in, gets hotter and hotter and hotter and can emit enormous amounts of light. Okay, and so it was proposed that 3C273 was being powered by gravitational processes, okay, by material falling onto a massive object. Okay, but how massive? And so to get some idea of how massive it is, they use something known as the Eddington luminosity. And what this states is that as material falls towards a massive object and it heats up, you get a quantum effect, which is where the photons try and push back against the material that's falling in, okay? And you can get a situation in which you have as much pressure from the photons pushing back as you do have gravity trying to pull the material in. And eventually you get an equilibrium situation. So that defines the maximum luminosity that a gravitational system can have. Okay, so I'm going to use my board again for the second time to show you what this corresponds to. Okay. So the maximum luminosity that an object can have corresponds to, if you write it in solar units, okay, we can have the maximum luminosity, okay, for a system such as a black hole, okay, if it's got a mass of 3.2 times 10 to the 4, okay, so that's the mass expressed in terms of solar masses, okay, and that's the luminosity expressed in solar luminosities, which means that the luminosity of our system must be lower than the maximum luminosity, which means that our luminosity, okay, so if our maximum luminosity, if we say that is equal to 3.2 times 10 to the 4, okay, and that's in solar luminosities, and that's in solar masses there. We can divide, so if we divide 3.2, that our luminosity divided by 3.2 times 10 to the 4, okay, that gives us a lower limit for our black hole mass. And if we do this for 3C273, it turns out that the mass of the compact object 3C273 must be greater than about 10 to the 8 solar masses. Okay, from 10 to the 8, so that is 100 million solar masses packed into a space, because we know that this thing's varying on timescales for about a day, packed into something roughly the size of our solar system. Okay, and so this is well above this 2 solar mass limit for a neutron star. And so this means that we've got these, this implies then, because it's much, much more massive than a neutron star, it implies that the only thing that it could be is a black hole. But rather than being a black hole that is sort of stellar in size, or stellar mass in mass, it'll have a kind of solar mass in size, this thing has got a mass not of 10 solar masses, not of 100 solar masses, but of 100 million solar masses. And this was really the first strong evidence in favor of black holes in the universe. Now, after the discovery, or after the interpretation of what 3C273 was, it was realized that this wasn't the only object in the universe that was like this, but actually there are many, many more systems in the universe in which you've got these black holes accreting material. And these became known as, this object that I study, these became known as active galactic nuclei, because a lot of them were found, or all of them I should say, were found in the centers of galaxies. And so they became known as active galactic nuclei, and active because they're releasing so much energy. Some people at the time proposed, well, is there something special about these particular galaxies? Okay, maybe it's only these active galaxies that we see that have got supermassive black holes in. But then other people suggested, well, actually, maybe it's the case that all galaxies have got these supermassive black holes at the center of them. Okay, and it just so happens that only some of them are accreting large amounts of material at any given time. Okay, and so what that implies is that there must be large numbers of dormant black holes in the universe somewhere. Okay, so every massive galaxy contains at their centers a dormant supermassive black hole. And so the hunt was on to try and find these dormant supermassive black holes. With the launch of the Hubble Space Telescope, what we were able to do is we were able to measure the movement of stars very, very close in to the centers of galaxies. And when we did that, what we found is that the motion of these stars was consistent, entirely consistent with all of these nearby galaxies containing at their very hearts, whether they had an AGN in them or not, containing at their very hearts a massive compact object which was entirely consistent with a supermassive black hole. In that case, what about the Milky Way? I'm just going to show you a brief movie here to demonstrate what some work, so the work that the people who won the Nobel Prize earlier this year did in the 1990s. And so what they did is considering the results that we've been getting looking at nearby galaxies, they thought, well, if that's the case, shall we try and probe into the very central regions of our galaxy? And so they performed what is quite an amazing feat. they trained some of the largest telescopes in the world on the very central regions of our galaxy. And what they did is, over a period of years, they kept on going back and measuring the stars, measuring the positions of stars in the center of our Milky Way. And what they saw over time is something that looks like this. Well, actually, these are the observations that they obtained. They saw these stars circling round a region in the center of our galaxy. Okay, so there's clearly gravitational attraction going on there, but we don't see a bright source there. So that was confirmation that at the very center of our Milky Way is a very, very massive object, and we can calculate what that mass is, and it's roughly 1 million times. I think it's 4 times 10 to the 6 solar masses is the mass of the black hole that sits at the center of our galaxy. Okay, and so also around this time, what astronomers started to do is we started to consider, well, shall we measure the masses of these black holes within these galaxies, and we'll have a look at the properties of the galaxies that contain these black holes. And what they found when they did that was that we find that there's a very tight relationship, okay, over many orders of magnitude. Okay, so this is going from black hole masses here of only 10 to the 6 or 1 million solar masses, okay, up to 10 billion solar masses up here, over 4 or even 5 orders of magnitude, a very tight relationship between black hole mass and the mass of the galactic bulge. You might say, well, so what? Just means that massive things live in massive things. Okay, so this is the properties of the galaxy itself, and this is the property of the black holes. What's interesting is that most of the galaxy, okay, doesn't know that the black hole is there in terms of its gravitational influence. Okay, there are far more stars within the central region of a galaxy. There is far more mass from stars in the central region of the galaxy than there are black hole. So by the time you get out to the size of a bulge of a galaxy, those stars in that bulge aren't aware gravitationally that the black hole is there. So the question becomes, if that's the case, how is there such a tight correlation between the two? Okay, and so what was proposed is that in order for this to be the case, our black holes must be having some kind of influence on the growth of our galaxies. But how? Well, one proposal is that the amount of energy that is being released by these growing supermassive black holes when they form these accretion disks is sufficient to switch off star formation within their host galaxies themselves. And so it's been said that galaxies at their very centers contain like a time bomb that is sitting there and waiting to stop our galaxies from growing. And in actual fact, our computer simulations, and there are people in Durham, so Richard Bauer is very famous for doing this kind of work, who work on the simulations that have been in which we have to use powerful active galactic nuclei in order to switch off star formation in these galaxies. And if we don't include this energy, then we don't get the correct results out. Our simulations don't look like what we expect them to, or what we see in the real universe. Okay, so you can have these outflows, these powerful outflows, extending into the galaxies and switching off star formation. And some outflows, these radio jets that we see, okay, can extend not just over galactic scales, but on intergalactic scales. Okay, so hundreds of thousands and even millions of light years across. Okay. So one of the key problems, however, is that we see these outflows, but we still don't know for sure whether they are actually having a key influence on their black holes. So the simulation's predicted, but there's a very active area of research at the moment in AGN astronomy and in black hole astronomy to identify the switching off the star formation within these host galaxies. So that's one very key area of research that's taking place in black hole astronomy. Another key area of research started around about 10 years ago was when we watched the nuclei of galaxies that didn't contain active galactic nuclei in them. Okay, so they were just they were galaxies whose supermassive black holes weren't actively accreting, but once in a while, if we kept on watching them, we'd see flashes of lights from these galaxy nuclei. And what we think is taking place there is you have a situation where you've got a supermassive black hole and a star has ventured too close, and the star is starting to be ripped apart by the gravitational pull of the supermassive black hole. And so there's going to be a very keen area of research. And if you're interested in going into kind of astrophysical research, this is going to be a very keen area of research over the next few years. Another key area of research is using quasars to peer right across the universe to try and identify the most distant object in the universe. And this is one of the most distant quasars that we've ever observed. Okay, it's observed at a redshift of 7.1, which corresponds to when the universe was only about 770 million years old. And yet this black hole has got a mass of about 2 billion solar masses. And it's a real puzzle for us astronomers at the moment, for us to work out, well, how on earth did we get a black hole to grow to 2 billion solar masses in only 770 million years? Because all the time it's fighting against this Eddington luminosity. Okay, there's a regulation effect going on there. And so it's a real puzzle to know how they grew so quickly. Some people proposed that they start off from primordial black holes that have got masses of 10 to the 4, even 10 to the 5 solar masses. But if that's the case, where are they? And this is a huge puzzle within black hole research. Okay, we've got lots and lots of so-called stellar mass black holes, but where on earth? And we've got lots and lots of these supermassive black holes. But if these supermassive black holes started off with masses of 10 to the 3 or 10 to the 4 or 10 to the 5 solar masses, then where are all of these things now? What's happened to them? And so that's another key area of research that we'll be kind of investigating over the next 10, 20, 30 years. And the final thing I just want to briefly talk about, I know I'm kind of running slightly over time, but this won't take very long at all, is that, so I've talked about how black holes were discovered, I've talked about their importance for our understanding of galaxy evolution and formation, I've even talked about some of the puzzles that still surround black hole research today, but what I haven't talked about is the future of black holes. Because actually the future of the universe is a future in which it is dominated by black holes, okay? And so, eventually, after long enough time in the universe, stars will start to go out because they will start burning through all of their hydrogen, okay? And eventually, you'll have a situation where all of the material, all of the baryonic material in the universe will eventually collapse and fall into a black hole. Okay, either that or that material will, the particles will decay into photons. And so roughly in about 10 to the 43 years time, all of the whole of the universe will only contain supermassive black holes or massive black holes and photons. That will be the only thing in the universe, because all of material will have fallen into, by that point, black holes. There'll be no more stars, because all of the stars will have burned through all of their hydrogen and ultimately will have fallen into these black holes. Now, what's interesting is that this future universe, if our theories are correct, this future universe will last for about 1 trillion times longer than all of the previous phases of the universe. And so actually, if you were alive in 10 to the 43 or 10 to the 50 years time, what you'd be able to say is that the universe, to a very good approximation, or at least for 99.99999% of the history of the universe, it has just been photons and black holes. And we will be a very distant memory. And I'll end it there because I've already taken up a bit too much time.